All right, well, we're staying along the lines of the transportation topic. I will say just before I start, to Dr. Kilroy's point, the expansion contraction of bridges is very important. My second month on the job at HNTB, I ended up working for one of the longest span bridges in the continent, and the finger joints that expand six feet plus or minus to allow movement had gotten bound up, and we had to respond to that. So that was my trial by fire initially when I joined the bridge industry. So today I want to talk from the practitioner's perspective, the bridge engineer's perspective on extreme rainfall specifically, and the way we've been able to use NOAA's data to better understand and quantify this risk. My entry point to this was Hurricane Ida, which is shown here on the screen. That's me with a backpack, looking a little bit more confused than I probably would have had I known the picture was being taken, but the local news kept using this photo over and over again, and so I decided to sort of use it as my demonstration here. And so as people walk below rail lines where gravel had been just 24 hours before, it really dawned on me sort of three things. One was the very visceral effects that extreme weather was having on infrastructure. Secondly was the cascading impacts of these events. Suddenly the single 12-foot span failing stopped all garbage trains from getting out of New York City and tens of thousands of commuters from getting in. And the third thing was the hidden vulnerabilities in our system. This culvert was one of many dozens on this line that were all would have looked identical going in. And so this presentation today is really my reporting back on my journey so far through NOAA's data and getting to know many NOAA software engineers and data scientists and meteorologists. And so really trying to talk about what that has meant to me as a bridge engineer and how it's informed my decisions. I'll just say I'm not an academic, I am not a scientist, but I've gotten to know many of them, and that's been very exciting. And so maybe the last thing I say before I sort of go into my very brief bio is that the transportation sector differs from the vertical construction in a couple key ways. One of which is that if you're a homeowner, you have a discrete point on the map that you care about, and you're crossing your fingers not to see risk. But these transportation agencies, they have in some cases tens of thousands of assets distributed over hundreds of square miles or thousands of square miles. And so there's almost a near certainty they will see the highest level of risk somewhere on their system. And the second thing for transportation is that there is no insurance policy in the conventional sense. If there's failures like these, it's not an insurance claim, it is instead cascading impacts through society. And so just my background, let's see if I go here. There we go. My background, just very briefly, I've been at my company, HNTB, for about 15 years. Been fortunate enough to be a designer and inspector, worked at a construction support, data analytics, and then also now helping to close out some of the larger jobs. That's why really my conventional background, and ultimately my goal here is just to design safe bridges. My other background is that at HNTB, I also serve as someone who's taken on the role of bridge technology lead across our firm. And so initially that meant things like sensors, tell us how much the pier is tilting back and forth or strain gauges. But instead, that's really morphed into any data set technology or innovation that affects bridges and their risk now falls under really what I'm trying to better understand and quantify. And so being able to explore all these ideas has brought me into contact with numerous other adjacent areas, including data and climate science, meteorology, cloud computing, and many other areas, none of which I am an expert in, but all of which I have built a working knowledge of by helping and understanding with experts in these fields. And so the key data set that I want to talk about today is the multi-radar, multi-sensor data set put together by NOAA. This is the best of the radar and rain gauges integrated into one cohesive GIS layer. And it's about a square mile granularity, and it's also available on an hourly basis for rainfall accumulation. This is the first data set I really came across and dove into. And I've been able to communicate with numerous NOAA scientists who have been involved with this data. And so I really want to articulate the practitioner's perspective on why this data set is so key, ways that NOAA has been able to democratize access to it, and also how it can help us to quantify isolated extremes and helps us to inform the strategy as well as risk. And so this here is a view of their operational viewer, just to show what this looks like, and there's many numerous sort of layers and data filters, besides accumulation, including the flash flood program. And all of this is put out by NOAA's National Severe Storms Laboratory. And so one example that we saw was a bridge we knew had washed out in Indiana. We went back and looked, can we find that data on the map? Boy, could we. The image on the left is not radar data, but instead colorized rainfall accumulation. And that spot that was shown there saw 10 inches of rain in 6 hours. Just an ungodly amount of rain is what caused this bridge to wash out. And what stands out for me most is not the bridge washout, not the intensity of rain, which I think well exceeded the 1,000-year return interval, but instead the extreme isolation. Only a few miles to the east, almost no rain fell at all. And yet here we have this historic level of rainfall in that red dot. And so this is the case, and we're relying solely on rain gauges to inform risk, both near term and over the long term. We may be missing key extremes like this one here. Now, we found out about this one by the local news. Certainly social media has played a role in helping to transfer information from the public to authorities during extreme events, but we don't want to be relying upon local news and social media to quantify either during a storm as it's happening or historically on what has occurred in the recent past. And so using the multi-radar, multi-sensor data to cast a wide net over a multi-year period on multiple states of the extremes they've seen over multiple durations of time, 1 hour, 3 hour, 24-hour storms, we can put on new glasses and lenses to understand this risk. Now, those glasses are a little bit blurrier than our rain gauges that we typically use, but instead of looking at the world through a straw at what happened at that one point in space, I can see the entire scene laid out before me. And so this is all made possible by NOAA's Open Data Dissemination Program. This is a systematic effort by NOAA to put much of their data into the cloud in a consistently named, fully and continually accessible method, and in partnership with Azure, AWS, and Google Cloud, and it's also free egress, which is a huge deal given the size of these files. And so the challenge I faced is that I had a key data set and an easy way to get to it, but I could only get to one file at a time. And so if I wanted to know what happened over multiple durations, I had to pull down for, let's say, a year, 8,670 different GIS files, one for every hour of the year. And that's really what's shown on the left there, is that we cover the whole continental US, but we're doing it in one slice of time after another. And so my core collaboration with NOAA has been to transform these slices of times into the arrows shown on the right. I initially put together a Python script that went through and was able to convert those GIS files into a tabular data structure that allowed the querying of a given individual point. So I could see hour by hour what happened at an exact location per the MRMS data set. To their credit, teams at North Carolina's Institute of Climate Studies, NCICS, as well as NCEI, and then eventually the IPG, Industry Proving Ground, were able to take my workflow that I did as just a demo, use that code as the beginning, and actually make it much better and more efficient, and now have implemented it in a public-facing way. So IPG, which I know a number of you are on the advisory panel with me for engineering architecture, we've been able to create this workflow so that anybody can access with the correct sort of querying language through Python for any given point in the US, the historical and near real-time data for a given point. We've actually built this in a way that's so efficient. I was able to get, I did a time check on myself, all of New York State for the year 2024, I could get that data from the cloud onto my computer in under 2 seconds, something that would have taken 24 hours of post-processing in the GIS side to be able to do. And so with this type of data, we're able to look at things like this, where we have multiple durations of time. I can look at the peak 1 hour, 3 hour, and 24-hour peaks for a given point in space. This happens to be a bridge that washed out during Hurricane Helene, and we can see just how devastating that was. 8 inches of rainfall in 24 hours at this bridge. But we can also see the significance of how much this hurricane stood out compared to the extremes that we're seeing in the rest of the year. Now, the question I always get from hydrologists is, one point in space doesn't tell me the story, can you do it for watersheds? And the answer is yes. We've been able to use the USGS StreamStats program, draw the boundaries around an area, and actually average the watershed rainfall in a similar methodology to this as well. And so a single point in space is okay, but what about the entire set of bridges? So what we did was we took the National Bridge Inventory, 600,000 bridges, we paired it with NOAA's data sets that they democratized and made into that queryable format, and made a cloud-hosted data pipeline to actually structure how can we look at all of these rainfall data sets. And so while it remains proof of concept, while it remains preliminary and just a demo, we've stood up a dashboard that can look at every single bridge in the country and show in near real time a 30-day window of what peaks have been seen. Now, what's incredible to me is if I had heard that existed a year ago, I would have said, okay, which academic institution, which federal agency has stood up this 600,000 point dashboard that's maintained in near real time? And the fact is, I was able to do it on my own because of what NOAA has done. That's not to say I'm so special. I'm actually very average. I'm a bridge engineer who taught myself Python. But because this is available through the cloud, because the MRMS data set is so granular, and because this has been now democratized through IPG, something like this can be possible for any user who goes out looking for it. And so I want to get to talk a little bit more about risk and how we're able to use this to better quantify risk to a population of bridges. This is the state of North Carolina, every single bridge in the state, and it's the 1 hour peak rainfall. And so what I don't like about histograms is that we're able to see where the bulk of the rainfall is, but this very small piece out here, the outliers, barely stand out, these 3.5 inches of rain in an hour. So what we tried to do was we took every single bridge and we made it a dot. And we said, if we have all these dots, how can we actually look at them and understand the amount of rain that was seen as a peak at every single bridge? And right now they're in arbitrary order. So this dot up here, this bridge, saw 3.5 inches of rain, and this one maybe 3.25. Now, moving that over to the left and then putting these in ascending order, we see a very clean picture emerge of what is the risk profile for this set of bridges. It's essentially an extreme value distribution sort of turned on its side just because of the way that we've plotted it. But we're able to see that this last few percent of bridges see a hugely disproportionate amount of rainfall compared to the rest of the bridges in the population. And the challenge for me is that we have no meaningful way to know where or when those are going to occur, these extremes. And so this is North Carolina for 1 hour. This is North Carolina for 24 hours duration shown over a 4-year period all the way through 2024. And we're actually able to see, we compared every single bridge location to its Atlas 14. So again, just to say this a little bit different way, they look like lines, but it's actually just a very closely spaced bridges. This is every bridge in the state of North Carolina, and we're taking the peak 24-hour rainfall that was seen at every single one of those 18,000 bridges. We're showing what that extreme looks like and these tails, and we're comparing it to the Atlas 14 100-year storm at that given location. What we see is that because of not only Helene, but also an event that happened a few weeks before in the southeast portion of North Carolina, 6% of their bridges exceeded their 100-year storm, where it is in the previous 3 years, only about 7% have. Now, we've looked at numerous states over a multi-year period, and on average, about 1% of bridges exceed their 100-year storm, which stands to reason statistically. But what that means for state agencies who have to oversee these is that every bridge in a given year is essentially rolling the 100-sided die to see if its number is up to see this portion. It stands out to me that some of these bridges are seeing nearly 80% or more than 80% of their 100-year duration, which obviously is on a log scale, and so it's well more than 80% of the 100-year storm. It's not a 180-year storm, it's more like a 1,000-year storm. And so much of the effort to make bridges stronger is certainly warranted. We want to prioritize the best available resources and funds. But if we're only making things 20% stronger, there will still be a significant portion of bridges that well exceeds that amount. And so here's my core idea that I want to present to this group, is that the high resolution data sets that I've mentioned are invaluable for adapting to non-stationarity despite the brief historical window, the 5 years. And I know this probably causes qualms among this group, potentially. Certainly, I'm not suggesting we're adapting our design criteria. I'm arguing we can adapt our strategies and the way that we quantify risk in the near term for these ways. And so again, this is my perspective from a practitioner's perspective. And so updating our design criteria is great. The challenge is that many DOTs and agencies have the majority of their effort, time, and energy and resources go into existing assets, which were not built to the updating design criteria. Many of the worst extremes well exceed that 100-year storm, which we showed for a certain number of bridges. And because it's so widely distributed, there's a high likelihood some on the system will see well beyond that 100-year return period. There's minimal fleet turnover of existing assets, either meaningfully retrofitting them or being able to replace just based on limited funds. And so what I'm asking is how can we use these high resolution data sets, which better quantify risk on a broader geospatial basis to understand if new strategies are warranted and to consider how they would look. Now, one thing that many states have done, and some of these that go back to federal mandates, is to look at vulnerability assessments of their inventory of assets. The challenge that I foresee is that nothing in the inventory of assets can withstand 10 inches of rain in 6 hours. And we are seeing this happening more often than it has in the past, at least by the data set window that we currently have. And so I'm all about finding the most vulnerable assets and the most critical ones. And there's always a few that rise to the top as just the most absolutely critical. A scour critical bridge, perhaps, where it's vulnerable to water and flooding that leads to a hospital is the only route. absolutely vulnerable, absolutely critical. But once you take care of that top 5 or 10% of risk, the rest of the 80% in the middle really looks very, very similar, and it can become very subjective and subjected to which assumptions are made on criticality. And so even though every asset has a low chance of seeing that 1,000-year return period event, it's almost certain that some of them will on this distribution. And the fact is that some states already struggle to meet the current standards that we have. And so in the little bit of time that I have left, I want to just go over a handful of strategies that I've come across that seem the most promising to me. You know, as someone who is only 15 years into my career, I've got another 30 years left. And so what I'm trying to find strategies that look the most promising to me and trying to see if I can find the economic justification for those strategies within the extremes that we're now able to better quantify because of MRMS data. And so these are each of them. We'll go through them one by one very briefly. This photo on the right, though, was taken from Hurricane, I believe it was Hurricane Harvey in Texas in 2017. And per National Academy's NCHRP study, this was a 250,000-year return period event. Now, when we get to 250,000-year return period, that is a number that is hard for practitioners to understand or quantify, and it's challenging them to really integrate these ideas of how to use these design criteria into their head. And so the first strategy would just be better improved situational awareness. NOAA puts out their HER model, the high resolution rapid refresh. They put out their accumulation of the MRMS data we talked about, and they put out the how much has accumulated compared to flash flood guidance, a metric taken from the National Water Model. They put out all of these in near real time on a continual basis, and it's available in the cloud. While it's, again, concept level, we've created initial cloud-hosted pipelines that every time a file is posted, we download it, tabularize it, check it for given thresholds that we've set, and then can send auto-generated emails to given stakeholders if that's the case. I'm not trying to be a meteorologist, but if it's only, I did the calculations about 7 cents per day to maintain this pipeline for me to get near real-time information and the exact method and threshold that I want, that is something that certainly could provide value. We've heard from some states that they have challenges when these events go through. They don't even know where to send people, where to get boots on the ground. So understanding where these extremes occur in higher resolution detail may help them to better distribute a limited resource of personnel during that time, as well as allowing hydrologists to better understand what areas and timeframes and durations they should be analyzing. A lot of talk about resilience from Dr. Kilgore, and absolutely valuable insights that he had. This is the curve that I always go back to, that I sort of try to summarize resilience in one key graphic. And it's losing functionality of the system and then eventually restoring it. And so much of the work we do is built on making as many assets as possible stronger so we can change the resist portion, the depth of that curve. What I argue is if we can find ways to restore assets in a shorter amount of time, we can actually make the curve smaller in the time duration, maybe in addition to the depth duration. And so when I say rapid bridge replaceability to bridge engineers, they oftentimes sort of roll their eyes at me. We think of things like an Acro bridge or a Bailey bridge or other methods where it's a temporary construction bridge. What we were able to do from that washout that I responded to is that my colleagues were able to design a bridge that after the contractor signed on, it was only 6 weeks before we had trains running in that structure. And this is an innovative approach which minimizes work in the field and the number of materials necessary, the different types of materials. So within 6 weeks, we had trains running on the structure because we had to get trains in and out of New York in a more effective way and at the full capacity of the rail line. So we were able to make this work. We've now used it in several other locations as well. This group is no stranger to fattening tails and extreme value distributions. What stands out to me about the MRMS data set is we're able to actually quantify those, the fattening tail, in ways that go beyond what we can do with rain gauges. And so this is just one conceptual methodology we pulled together, which is we looked at any time there had been an exceedance of a 25-year and 100-year storm in a given state, and we've now put these onto a GIS file. But what this allows us to do is understand the characteristics of the events that are occurring that are causing these exceedances. Is this a hurricane? Is this a microburst or a rain bomb that no one would have seen coming? And so being able to quantify the types of events that we need could help us to modify our strategy. Looking at forensics, as an engineer, I have two thought processes. I want to know the design or the demand on my system, the load, and I want to know its capacity. If we're able to, with better rainfall analytics, understand the demands more in higher granularity, we can then actually create a better forensics as we perform them. This event here was the Leominster event in Massachusetts in, I believe, 2023. And we saw a number of these shaded green ones exceed the 1,000-year storm. We're only 2 years away. We didn't even hit the 100-year storm. And 2 of these 3 bridges actually were damaged significantly during that storm. Now, this is, I think, my second to last slide here, is that many of you have probably heard this analogy, but during World War II, they tried to understand where they should be putting additional armor on the planes. They collected all the locations where they had been bullet holes, and they started to go put the armor in those places. And then a group of statisticians at Columbia said, actually, the places that the bullet holes did not strike are the planes that were not coming home because they were fatally struck. It was survivor bias error. And I feel like as engineers, we're tempted to make the opposite, the sort of inverse of that assumption, which is we spend so much time looking at the types of bridges that have failed and don't spend enough time looking at what bridges have seen well beyond their design criteria and yet have survived completely. Are there entire classes of structures or types of assets that we're able to look at holistically at the way they've performed and maybe well outperforming our expectations? Is implementing more of those types of structures something that we should be considering? And is that what resilient design looks like? And that is much more possible based on the granularity of the MRMS data set and its demands. And then finally, looking at ways we can look at site-specific design considerations. This is images of a bridge we put in a flume. We found out that during the 200-year return period interval, this bridge would be overtopped. We wanted to understand what those demands would be and found that actually the governing case, the worst vertical downward load on this bridge would be when the water was overtopping it, not when there was the heaviest truck or pedestrian loading on this bridge. So we're able to look at atypical design demands on our structures. We're able to look at details that make it so bridges are safe to fail and they're able to fail in repairable ways, as well as look at ways that we can justify economically future augmentation options within the bridges. And so in conclusion, I'll just say that my sense at least is that the high resolution data set put together by NOAA, democratized by IPG, made available through NOAA's NOD program, could provide invaluable insights to practicing engineers as they try to adapt strategies as well as risk quantification for non-stationarity. Thank you.
All right. Thank you, Erik. Excellent. Good stuff. Questions for Erik? Yvette? I can't, yeah, I think you're on mute, Yvette. I know you're having a little bit of problem, but what combination will work? I don't know what to tell you.
Can you hear me?
Yep.
Yeah.
Good.
Okay. I think I'm gonna have a little feedback, but I'll see what happens. It was very interesting. Thank you very much. I did want to, oh gosh, I'm getting a lot of feedback. Hold on. I did want to ask you about some of the assumptions on risk. As we're getting to a situation where I think there's going to be a lot more emphasis on establishing like what's the real risk? What are we willing to tolerate? How much damage are we willing to tolerate before we make those investment choices? I want to go back to like your example of the bridges. If it's a bridge that has it failed, but it's the only time it's failed in the last 50 years, are we willing to accept that risk? Is that part of your model? How are you thinking that we should be moving forward to think about that?
Yeah, so I would say, the current 2 playbooks that I sort of talked about, one was the making your design criteria better, and the other one in parallel was finding ways through sort of risk-based asset management, as Dr. Kilgore mentioned, to use funds that we have in the best possible way. What I think this risk can do is help us to understand even beyond those 2 methods in the current time frame until we get sort of there, wherever there is, what is the risk that we face? And do we need to invest in strategies that help us to mitigate or sort of buy down the risk that happens? So rapid replaceability would be one example. I think if we're able to understand how often these are happening, especially things like microbursts that don't get headlines, don't get necessarily even noted. Sometimes they just happen in the middle of a cornfield and no one even knows that it occurred. If we can better quantify those, we can articulate the risk that is faced by the population and then help to understand what the strategy should be, and then make those tough decisions of what risk do we find tolerable. If we can make sure that no people are on the bridge when it goes down by maybe blocking the roadway, we can replace it in a sort of only single digit number of months time frame. is that a risk we're really forced to or are willing to tolerate?
Joe Barsugli.
Hi, thank you very much for that presentation. And this ties into some of the work that's done here at Series in Physical Sciences Lab in NOAA about heavy-tailed distributions. So, I mean, part of this, when I hear things like 250,000 year event, I mean, we simply do not have the data or even the models. That to me, that's a fiction.
It is. It was in a National Academy's report. It's report 975, and that's the only reason I mentioned it. Otherwise, I wouldn't have brought it up. I'm assuming that it was extrapolated along the log distribution.
Well,
that's where
I mean, we're trying to fight the battle that shouldn't even be used.
Correct.
As you say, it means that they're using the wrong distributions. But so I really like the work you did, and you showed the thing about the heavy-tailed distributions. So it seems like that might be the biggest. I often think that present-day risk is underestimated because of the use of these distributions, and this seems like a really, really useful tool to do that. But the question I wanted to ask was about going a little bit deeper into the short time record of MRMS. And I mean, I thought you handled the answer well, but the question is, like, in Asheville, the 1916 storm was nearly as big as Helene. And is there any way, I mean, I don't know if you've thought about how to combine those or maybe to take advantage of some of the longer, deeper records.
Yeah, there are other data sets that I'm aware of that go back well beyond the 5 years. They're not as granular in most cases. The good and the bad news is that NOAA has been, as you know, continually making their software and their hardware better, which is great for getting better accuracy, tougher to look back historically. We have talked about looking at, the 5 years of MRMS and then maybe, 30 years of another data set and overlaying them to try to understand and look back historically at how those go. I will say that again, the majority of my time and much of my sort of perspective is shaped by interacting with more than a dozen different transportation agencies over the course of the past year. Many of them, let's say, are trying not to use things like projections, maybe in the way that they formally go on the record with some of these decisions. However, identifying observed extremes and how they compare to current design criteria allows them to make a better justification for additional resources outside of the track of thinking about projected extremes.
Thanks.
All right, Bilal.
Yeah, thank you, Eric, very much for your presentation, as well as I'd like to thank Roger for his presentation too. My question is about, first of all, your work is really outstanding. I enjoyed the presentation, and but it's obvious you are focusing rightfully on the hazard. So everything you've done is hazard, basically extreme rainfall and so on, which is a component that's definitely needed for evaluating the risk. But it's not the only item which is needed for evaluating the risk. We need to know the capacity or the strength side of the bridge, which means you have to get to the particulars of the bridge. So, for example, a designer could meet the requirement, the standard requirement, and if we have an extreme event, doesn't mean the bridge will be will fail. It depends on the drainage system and the layout of the grounds and so on. All of that characteristics of the site has to be brought in. Always we have the loading and we have the strength, the capacity. Now there is a chance if we know the details of the bridge, we'll be able to calculate the risk. And risk is defined as potential loss. So there has to be a loss, which means I need to know the strength. So I could see as the logical, next step, and there are 600,000 bridges. So to look at the site characteristics and the drainage and so on for each one is a tall order. But I wonder, so to what extent is a violation of the minimum or the design requirement in terms of precipitation will actually lead to a failure? And to what extent bridges could be enhanced so that their designs are dominant, tolerant for extremes, much more tolerant. When we did a project in Mozambique, that was the strategy that was followed by the design team, is to basically come up with a design that even if we get any flow level under the bridge, it's not going to affect the bridge. So it becomes, the design architecture of the bridge to enable being tolerant to those extremes. Thank you.
Yeah, I would say, the way that we're thinking about that, and again, to your point, we really focus on the demand. We have not looked as much at the capacity. The things that we're thinking about are things like integral abutment bridges, where the beams themselves are actually cast into the soil. It's a little bit challenging because of that expansion contraction, but it does end up being, for 1 and 2 span bridges, a very robust structure that we're able to use. So can we use the better quantified demands and look at the inventory, right? Divide into integral versus non-integral, and understand, are they outperforming on a population of assets. The only DOT that I'm aware of that's really done anything similar to this is North Carolina, and they actually looked at, I think it was Matthew and Florence, that went through with the MRMS data set, or maybe another granular data set, and looked at the characteristics of culverts that had failed versus not failed in the thousands for each one, and looked at those unified characteristics. And that was the piece that they were able to sort of try to divide out which of these site characteristics and asset characteristics are helping us versus hurting us.
Interesting. Just one last comment. I think another approach that we followed in the bridge in Mozambique is to ensure that there are fuses, that wherever it fails, it's at predetermined locations that are easy to repair, which is going back to your item about repair.
And there are times we make the approaches of the bridges weaker, or maybe the low point compared to the bridge itself, so that will give way and it's just soil and the bridge stays intact.
Very good. All right, Roger, I'm going to give you one last bite so we can get to Tom.
Okay, just real quickly, a very good presentation, Erik, and you touched on a number of things. Criteria exceedances, we do know that that's not necessarily associated with failure, and one of the things that the climate risk screening that I think Bilal was talking about, we have 2 items, sensitivity and criticality. Criticality is whether the asset is particularly important economically and needs additional present protection. And then sensitivity gets into when you have those high flows, what exactly does happen. And that is a more in-depth procedure that needs to be addressed. But the NCHRP 1580 project provides some guidance on how engineers on a large scale can assess those sensitivity and criticality to get a general idea of risk, to see what level of follow-on analysis is necessary. The other thing I think engineers need to, and Erik brings this out really well, you are virtually guaranteed to have a design exceedance during the lifetime. We know that engineers don't think about it in those terms, and I think that's an important aspect to get engineers thinking. And then you can address the next question as to whether the right level of risk has been selected. So I think all of those things link together and are moving towards improving our design processes.
And I'll just say it was really, an honor to present alongside you, Dr. Kilgore. Your work on 1561 really has been the go-to for so many states to better understand this area. So it's I'm really glad to be able to co-present.
All right. Thank you both.